All right. I think we are there. It's a quarter past, so let's continue. When it comes to the manufacturing of pipe, I said that the steel melt produces typically a billet, like a rod. And that would be the case for the vertical line that is colored. Sorry, what is on the left, because the manufacturing here follows what you can see is on the left side of this drawing. What is colorless is another type of manufacturing of pipe. As we see all the way to the top here is like a flat roll of steel that is being bent into a piece of pipe and then welded. Now, for most case, we are using pipes that are so-called seamless, and those would be produced from the billet. And typically all casings, tubings, liners up until the size, let me see, it varies a little bit, but I guess you can get all the way up to 20 inch if my memory serves me correct. Seamless pipe up through and included 20 inch. Anything above, and it's typically welded. But you can also get welded pipes that are smaller than 20 inch. But in the oil and gas industry, especially offshore, it's more common to use the seamless pipes for well construction. It's just typically conductors and these sizes, the very big ones that are made out of the the welded type of pipe. Now there is a third type that we can quickly mention. It's called line pipe. Line pipe, that would be pipes that are used for transporting oil and gas over long distances. Pipelines. And typically how these are made is welded, of course, like what's the process on the right, where there originally was a coil and then welded. But what is special about line pipe is that very often it is spooled into a huge drum. Then this drum is hoisted on board a boat or wherever you are laying your pipe. If it is in the desert, it will be on a huge truck. And then what you do is you stop whenever the drum is getting empty and you weld it together with the pipe on the next drum and you continue laying your pipe. Line pipe. Whereas what we see on the right would be pipes that are manufactured to specific lengths. Yeah, we'll quickly cover these processes. And I'll focus mainly on what we see on the left-hand side, the colored part. What we see is a billet out of the steel furnace. The liquid is poured into it probably has a very specific name, like a trough. Excuse me. And this trough is where you get the right temperature of the steel melt, and you pour it and it forms into a billet, a rod. What happens is that you put it through different mills with different shape in order to get the right shape, controlling the process of piercing the billet. In the center is like a spear, and that's what we see on the left-hand picture. It's where the billet is being pierced. It is being pierced and made hollow, and at the same time controlling the outer diameter of it, so that it takes the shape of a piece of pipe. Now, after this has taken place, there's a number of processes where it's rolled and milled in order to get towards the correct diameter and steel properties that we want in a combination. Now, what we will make a strong note of is the reheating furnace, and then the quenching. Quenching meaning that you drop the temperature either quickly or in a controlled manner. All of them influencing, and it because of, done to control the micro level, the atomic level of the steel, in order to get and acquire the right steel properties. There's also work to get the right size of the pipe, the right wall thickness, and also straightening the pipe. Sizing and straightening. And then as we are doing these things, we are doing what we call the work hardening, and we remember the graph of the stress strain curve, that we are going up until the point of where the steel is being deformed into the shape that we actually want it. Yeah. All of what is going on here is governed, in a way, it's correct to say governed by API standards, saying that an API standard is a recommended minimum, call it either it's a tolerance or a size, or it's pertaining to any property of the pipe. It will recommend that, saying that it should be this straight, it should be this wall thickness, it should be in this length, or it is something else than, well, you guys know, I guess, range 2 and range 3 pipes. That's what API involves itself with and recommends. It's not a specific way of doing things, it's a recommendation, and that's very important for you guys to note. We will look into the manufacturing recommendations from API when it comes to producing pipes, should we have time in this class. What I just realized was that we jumped over the overview of the class as per se. We're not going to spend a lot of time discussing the overview, but as you know, the basic material science is what we're covering today. The next class will be an introduction to the well construction process and talking about the casing setting depths and so on, casing design process, pipe properties and the manufacturing, of course, like just mentioned, pipe performance and modern calculation techniques. This one is well, one of my beloved parts of this class. Last year we added P&A and what it means to casing design, and we also added the topic of corrosion and how do we do with casing design and the difference between a field development and looking into each individual wells. This overview would typically change because of the call it the input of you guys and the class. What do you want to talk about? Where do you want to talk more or get more into depth? Do you have specific questions? Are there topics that we should cover? Think of this, call it what is in black. That would be the basic. What was in red was the request of the class last year. And good topics, so I just put them in for you guys so that you can well, request them again, or I will just lecture them. It's up to you guys to either replace them or keep them, or we'll see how much time we have, because if you ask a lot of questions related to the basics, then maybe we need all the time for just covering the basics. It's a little bit democratic, this process. Now I'm gonna presume that you guys know phase diagrams from analyzing and looking at hydrocarbons and insight into producing oil and gas. This is no different than the phase diagram of oil and of a specific oil composition. Only this is steel, as you may presume. At the bottom here, we have the percentage of carbon. This is 0.3% by weight carbon, and that produces a steel quality called 4130. It's just a mild steel, a typical mild steel, very often used in casing. And we'll go through what this phase diagram means to you guys. Think of it as going kind of in the opposite direction of this steel furnace. You're now at the melting position and you're going upwards. Only in the furnace you end up, you have at the top steel ore. And adding that as a side comment, what we call rust, the corrosion product of steel, that would be these two, hematite and magnetite, which will be what we are producing steel from again. So steel in its corrosion process just goes back to its nature in original state in nature. That's what it does. For us now, we're going to start at the bottom here, and we're going to follow the pure steel manufacturing process, going to the shape of a billet. What happens when the billet comes out here and it cools down? So here in this state, at more than say 1500 degrees, it will be a pure liquid. As we go down and cool it off, what happens is that we'll get at some point what is called austenite, which is a specific composition of steel plus steel melt. Going below into 1400 degrees Celsius, you will have pure austenite. If we go down to 800 degrees, we will have something called ferrite and austenite. This would be the two solids that the steel would form. When we pass this line called eutoctoid, I'm not sure I'm very good at pronouncing it, typically here at something around 700 degrees, you will produce mostly ferrite, but you will also have something called cementite. And looking at this point D here, what we will have is a composition according to what we call a leverage state or system. So this is the long arm, and this is the short arm. The short arm needing a lot more mass than the long arm. So you will have a little bit of cementite, whereas the main portion would be percentage-wise ferrite. And we will look into these different, call it composition and what they mean, the ferrite, the austenite, and the cementite. For your information and curiosity, and to have a peg to understand these things, cementite is the cast iron. If you have a wood oven at home or with a friend or in your family, or like the old engines would have their exhaust pipes, and some of the manifolds at least of the exhaust would be out of cementite or cast iron. It doesn't really have a very high, call it expansion factor when you heat it up. That's why you love it. It has a brittle nature, so we don't like it in many of our components, but we certainly have specific uses of it, like the oven. All right, I think we have explained this slide quite extensively. We will now look into what are the different compositions. The pictures that you see here, I'm gonna zoom in a little bit on first the austenite, or gamma as it's called very often. If we take a piece of steel that is austenitic, we will see that at the micro level it has grains. Typically where we see grains would be in a sugar cube. We see grains. Steel has grains just like a sugar cube when you zoom in extensively. Austenite has a FCC structure. Austenite is used, and we will see that in some steel qualities. Typically, some stainless steels would be austenitic. Several of our pipes used in wells, they are austenitic. Yeah, there's more information about the FCC here. I'm not gonna put any of those parts as exam relevant for you guys. They are just relevant for the rest of your life. That's what they are. So that's why I'm talking about them and giving them importance here. But in casing design, they are fundamental, I'd say, knowing and understanding this. They are so fundamental that they are not being taught. They are just understood in many ways, I guess. Cementite has a very specific structure. I'm not going to try to explain this structure for you guys. It's very strange. The purple atoms being carbon, and they go into the lattice with steel. So that's why it has this strange brittle and specific nature of cast iron. The BCC structure that we see here is a ferrite, and we see the grain structure of it, the white part being ferrite. So then we have an understanding of what is going on in our phase diagram that we just introduced. And being originally of coming from material science before I started in petroleum science, these 8 visualizations of what happens to a steel melt going from liquid until the final solid helped me understand how cement is behaving. When I first learned about how cement is setting up in annulus of a casing. We'll quickly cover it. The first one being around, say, 1500 degrees Celsius. You have a certain drive, energy for the steel to form solid, changing from a liquid state to a solid and forming atoms that are in the state of solid inside the liquid. Because you're having like what 90% liquid, few atoms, they have had the drive to change to solid. As you are cooling off your liquid steel melt, more atoms are changing from the liquid state until the solid state, and they are spread out through your bowl or cup or trough of steel, liquid steel. So they are here and there inside, floating around inside the liquid, growing. More atoms are changing, but they like to attach themselves to other atoms in the solid state. And we see clearly how they grow into irregular grains. As we have come down to, say, 1400 degrees, we have a complete solidified state. No more liquid exists. If we see a different composition of steel, say that you have 1% or even 2% of somewhere in between there of carbon inside your steel, you would actually have a combination of austenite and liquid. But with our composition, we are here, whereas the same temperature would be still at stage picture 3. When we cool down to stage 5, say, stage 6, we're starting to get ferrite. That would be around here, say around 800 degrees below the green line. And that would typically take place on the grain borders between the grains. That's when the solid state steel starts to change nature. It would no longer have the austenitic FCC structure, but on the grain boundaries. Grain boundaries being extremely important for the property of the steel specimen that you're producing. It changes from the FCC austenite until the BCC ferrite, what we just saw a micro picture of on the previous slide. Going down to below the eutectoid line, you have the state 8 here, and you will have a combination of ferrite and ferrite, and also you will have cementite, or what is called pearlite. Now these are exaggerated for you guys, so that you understand that even a solid piece of steel actually changes nature. It can change a lot, even in a solid state. Sometimes with some temperature, this can happen quite fast. At room temperature, the process still will take place, but it takes just longer time. Kind of important to understand when you're working with steel. You have a piece of steel in front of you, but it may actually be actively taking changes at the micro level. And that's kind of, yeah, as I said, important to know. We're going back to our process of manufacturing pipe. When we are milling, working the pipes, or the steel specimen, we are changing it at the macro and micro level. This drawing, and I will zoom in so that you see the milling better. It changes the grains from being nice small grains at random size and cohesion until elongated grains. And you can also think that the atomic lattice inside each grain is quite stressed by this. There is a lot of tension put into the lattices, so the steel on this side, on the left, before it is milled, has a complete different stress strain curve than on the right. On the right, it will be what we call work hardened or strain hardened. That's the general expression was in our curve. All of this taking place in the process of manufacturing the casing. In a way, in a miniature way, it also takes place while we are drilling, or while we are installing our casing. As we are drilling, I would say that it takes place in the drill pipe at a small level, because why? We want our drill pipe to stay the same as it was manufactured and as we are using it, and we're pulling out the hole, we want the pipe to be the same. But still, we are working the pipe. It has tension, quite high tension. It has sometimes pressure inside. It sometimes has compression. Yeah, or combinations of pressure and stress, just like casing. All right. We will go on and talk more about the micro levels here. We don't want the orientation level that we see after the milling. That is not desired. In absolutely the majority of cases, we don't want this at all in our specimens. We want a homogeneous property that that when we are torquing the pipe or introducing compression and tension in combination with pressures, that it actually is the same in all directions. That's very important to us. So what do? We just said that even at room temperature, things are going on inside a physical piece of steel. We heat it. We put it up from room temperature until these temperatures, and an accelerated process goes on inside. And all these oriented, big, elongated grains, they start to recrystallize. And new, beautiful, small grains are taking place. They grow and they become homogeneous. The specimen goes back to its homogeneous properties. Recrystallization by heat treatments. That's why, as we see on the right side here, on frequent basis, you reheat it to keep preventing it from going down. You keep it at this state, you work the whole specimen of pipe up here, you keep it there, you keep the temperature. As it goes down, it will keep as if the grains never were elongated, or so you rework the microstructure. And you can also do it by quenching or cooling it off and then reheating it and then recrystallizing. You have multiple options, and that is beyond what I'm going to lecture here. I'm just going to give you the insight that you can work from this end and preventing it from going down and keeping the properties of steel that you really want. What I can tell you is that when you introduce a whole lot of energy into these strains, into the lattices, into the grains, like milling would do, recrystallization by heating it up is a quicker process. When there's a lot of energy inside it. If there's a little bit of energy inside it, you would need more time to recrystallize. Yeah. More about what is going on when you deform a steel specimen into whatever you would like it to be, casing, a nail, a part for the automobile industry, whatever it would be. One of the failures or imperfections in a steel lattice is called a dislocation. You see a steel lattice in the picture below here, and it has a sign like an upside down T here, showing that a plane atom ends. And you will have like a imperfection in the lattice. These imperfections are crucial to the behavior of steel and the way of shaping the steel into casing or whatever you're doing. Thinking about the curve of steel, the stress strain curve of it. How it works. Putting a physical shear force sideways on a piece of steel, it makes these bonds jump. So the bonds that were on the right side now, they jumped over to the dislocation, meaning that the plane that was before coherent, it is now no longer coherent, and the dislocation is on a different plane. In material science, my old professor, he said, imagine that you're in a hotel with a very, very long hallway and you have a red carpet or a carpet going all along that hallway, and you want to shift it a little bit. What do? You make a bulge, and you make that bulge go along the carpet, and it's very easy to change it. But pulling at the very long carpet end in order to change it, it would be very hard because you need to shift everything at the same time. That would kind of give you the image or a mental picture of how steel is reworked easily compared to its actual natural strength. That's how milling works in a way. And we're going to take that back to the stress-strain curve of steel. Dislocations, as you have seen now, they typically work in the area here of what we call plastic yielding. Here is where dislocations are being activated. They are mobile and being activated, and steel is, well, you are at the yield of the steel, but you're not, as you see on the curve, you're not kind of putting more stress into it, but you're getting a whole lot of yield, a lot of strain, deformation, elongation. That's what you're producing at the same stress level because the dislocations are activated. Now, again, in this curve, it has been exaggerated for steel. Many steels, this part is not very visible or not prominent at all. It could be just a small nick and it goes straight over to the strain hardening phase. Dislocations, they are active and they are actually being produced when you go strain hardening of the steel. So when you are working and deforming your steel, the process of working and deforming it produces more dislocations. Dislocations are extremely important at the ultimate yield point where you go to failure. They are actually part of the fracturing process also, but all these things are, call it deep material science, and not extremely important for casing design. Why? Because we keep ourselves to this part of the graph for the reasons mentioned. We don't like our casings or pipes or whatever steel parts of the wellhead or valves or whatever we are designing. We don't want them to deform. We want them to stay exactly how they are. We talked about work hardening, and I'm gonna show that now on the graph how it works. If you stress beyond the yield point all up to this point P, the blue point A here being the yield point where you get 0.2% permanent deformation. Let's say that you stress it all up until point P. Then when you relax it, the specimen then has the new length here. This is its length. If you now want to start to stress the specimen that has this permanent deformation, the graph now starts here at the red line. The red line should actually go all the way into the center of origo. And if we go straight up here, up until the point P, and it will have the red graph here. The red graph should actually shift to the left. That is how the new steel would look. The new yield point is now P. Yeah. So that's work hardening. You go beyond the yield point and you get a new yield point, but you also have a permanent deformation that comes with it. The other manufacturing process is welding. Very often when you have seen a steel item that has been welded and has failed, you will see that it is typically taking place next to the weld. When you are welding, that takes place around 1600 degrees or more. It's a completely melted part. This is the weld in blue. What takes place in the ground material that you're welding together is that there is like a heat affected zone. What takes place where the ground material has not completely melted is an increase in grain growth. Grains are growing. They are melting together to bigger grains. Bigger grains, larger and more grain boundaries. Grain boundaries typically being weaker than the solid grains themselves. And whatever takes place on the grain boundaries here typically creates a much weaker structure than the base material and the original one. And the grain growth would be less prominent here and even less prominent here, and then so on until the base material is unaffected. So line pipe or what we call conductor would typically be welded, and then again the medicine and the mitigation to avoid the problems of having grain growth would be recrystallization. We have to do heat treatment. In this case, we go up on the graph. And new grains will form, the old ones would split up, and we will form a structure that is the same as the base material or the likes. Whatever we would desire, we can make it through heat treatment. Yeah. We can shape the pipe into any yield that we want in our process of manufacturing. Any yield point that we want, having ways of manipulating the yield point, the percentage of carbon, percentage of micro additives, manganese, nickel, chromium, whatever we do, and work hardening and heat treatment. Balancing everything out together, we get different yield points and different material qualities. I see the time is running out. I would just talk about a feature like magnetism. Some properties of steel that is typically steel would be influenced by these additives may influence the magnetism. Say that you freeze steel in an austenite condition, you quench it, you put it into water, and you freeze this structure. You put it from 1000 degrees and straight to room temperature, and you lock the austenite structure. You may have a non-magnetic structure, especially if you put in nickel, because one of the features of magnetism is that steel atoms, the electrons, everything spins in the same orientation, whereas a certain amount of additives like nickel would prevent this, meaning it would cancel out the magnetism as per se. There are many things we could talk about on material science. I think this is enough for you guys. Next time we will talk about external forces, how they act on steel. You would think it's a vector, but it is not. It's a 9-component stress tensor. We will talk about that and principal stresses and so on and so forth. I would like to take questions, even though we are 2 minutes on overtime. I will also talk about a video. You will also can see some of these things in the link to the YouTube channel from last year's lectures. My lectures this year will be kind of similar, only what you guys can do, you can ask questions to any topic. You can prepare yourself for the lectures by seeing last year's lectures, but few things will change. And we can make the lectures better by your questions. If you have any questions, ask them now, or we will see you guys on Thursday. Feel free to send email questions on my email, whatever you would like. All right, any questions? All right. Yes, next lectures. Looking forward to seeing you guys again. Thank you so much for your attention.
Maybe next lecture.